Welcome to another deep dive. This time we're going quantum. Get ready for a world where every decision you make spawns a new universe and where momentum might play a little hide and seek.
Sounds exciting.
We're taking a look at quantum mechanics, specifically the many worlds interpretation.
Okay.
And we've got a recent article that critiques a paper about whether MWI breaks the laws of physics. It's going to be a wild ride. What's really interesting about this one
Okay.
is it's not just about the science itself.
Right.
It's about how science is done. It's a chance for us to really sharpen our critical thinking skills and learn how to spot a questionable argument, even in theoretical physics.
Yeah.
So for those of us who aren't walking around with PhDs in quantum mechanics, can we break down what exactly the many world interpretation is?
Sure. So the many worlds interpretation, or MWI, is a way of understanding quantum mechanics.
Okay.
And it suggests that whenever there's a quantum event with multiple possible outcomes, all those possibilities actually happen.
They all happen.
They all happen, just in different branching universe.
Right.
So imagine a photon hitting a beam splitter.
Okay, yeah.
Instead of randomly going left or right, it goes both ways.
Yeah.
But each path creates a separate universe.
Whoa.
Yeah.
So every time I'm like, coffee or tea, I'm actually splitting into two versions of myself in a different reality. One sipping tea, one sipping coffee.
Exactly. It's a mind-boggling concept.
Yeah.
But, of course, it's important to remember that MWI is still just an interpretation, not a proven scientific theory. We can't actually test or observe these parallel universes.
Right, okay. So it's more of a thought experiment than something set in stone.
Right.
Okay, got it. Now, let's get to this paper that our article critiques.
Okay.
They claim that quantum mechanics violates conservation laws like momentum, which are kind of like the bedrock of physics. But then they're like, hold on. These laws are only broken on a single measurement level, and they actually hold true statistically over time.
Yeah.
And they're somehow connecting this to MWI. Help me out here. What's the problem with their logic?
Well, their argument is what we call a straw man argument.
A straw man.
They're criticizing a way of justifying MWI that nobody actually uses. It's like setting up a fake opponent just to knock them down. And the article we're discussing today calls them out on it, pointing out that this misrepresentation muddies the waters of the actual debate.
So why is it such a big deal that they use this straw man argument? It's just a theoretical discussion, right?
Well, it's important because it highlights a broader issue. It's about the way scientific claims can be distorted or oversimplified, especially when they're presented to the public.
Right.
Think of how often you see sensationalized headlines about groundbreaking discoveries that later turn out to be flawed or misleading.
Oh, yeah, all the time.
This article reminds us to be critical consumers of scientific information, even when it comes from seemingly reputable sources.
Yeah, you're telling me. It's easy to get swept up in the excitement of a new idea, but it's crucial to take a step back and ask, wait, does this actually hold up under scrutiny?
Absolutely. And that's where critical thinking skills come into play. We need to be able to identify logical fallacies, evaluate evidence, and consider alternative perspectives before accepting any claim as fact.
So even though this paper's argument about MWI is shaky, it does bring up this idea of momentum conservation in quantum mechanics, which sounds like a pretty big deal. Is there actually a genuine problem there?
There is a genuine problem there, but it's
Yeah.
not quite what the paper suggests. The real challenge lies in reconciling quantum mechanics with Einstein's theory of relativity, specifically when it comes to measurements and what we call non-locality.
Okay, now you're really getting into the deep end. Can you break down those terms for us?
Yeah, so think of it this way. Imagine a tiny billiard ball, but instead of having a fixed position,
Yeah.
it's kind of smeared out across the table, existing in multiple places at once. This is what we call a superposition in quantum mechanics. But the moment we try to measure its position, it suddenly collapses into a single definite point.
So it's like the ball is suddenly teleporting from this fuzzy, uncertain state to a precise location.
In a way, yes. And that's where non-locality comes in. This collapse seems to happen instantaneously, even if the smeared out ball was spread across vast distances.
Okay.
It's as if the ball is somehow communicating faster than the speed of light, which violates Einstein's theory of relativity.
Wait, so there's a conflict between these two foundational pillars of modern physics. That sounds like a pretty big problem.
It's one of the biggest mysteries in physics today. How to reconcile the weirdness of quantum mechanics with the seemingly absolute speed limit set by relativity.
Yeah.
This is where things get truly mind-bending and where physicists are still searching for answers.
Right, so we've got this intriguing clash between quantum mechanics and relativity, but I'm still curious about momentum.
Okay.
How does that fit into all of this?
Well, let's go back to our beam splitter example.
Yeah.
When that photon seems to randomly choose a path, it actually does carry momentum, but the
Mm.
momentum has to be conserved. Imagine the beam splitter is like a tiny trampoline.
Okay.
Even though it's much larger than the photon, it still recoils ever so slightly when the photon hits it.
So it's like a super tiny billiard ball collision where even though we can't see the trampoline move, it's absorbing some of that momentum.
Exactly. We don't always see the transfer of momentum directly because it can involve incredibly tiny objects and forces, but it's always there, upholding this fundamental law of physics.
Okay, so even in the quantum world, momentum isn't just magically disappearing.
Right.
It's still being conserved, even if it's on a scale that we can't easily observe.
Precisely. And that's a key takeaway from this article. Sometimes what appears to be a violation of physics is simply a matter of looking at the problem from the wrong perspective or not having all the pieces of the puzzle.
This is also fascinating, but I think we need to pause here for a moment and let our listener absorb all of this mind-bending information. We've covered a lot of ground already, from the multiverse to momentum mayhem. What are your initial thoughts on all of this? What stands out to you the most?
It's really remarkable how much we've discovered about the universe, but it seems like the deeper we go, the more mysteries we uncover.
Yeah.
Like we were just talking about how quantum mechanics clashes with Einstein's theory of relativity when it comes to measurements. This spooky action at a distance called non-locality.
Yeah.
My brain is still trying to wrap itself around all that.
It is a mind-bending idea, isn't it?
Yeah.
This apparent ability of quantum systems to influence each other instantaneously, even across vast distances, it challenges our intuitive understanding of cause and effect.
And you mentioned earlier that one potential solution to this puzzle is something called superdeterminism. Can we unpack that a bit? Because honestly, it sounds a little intimidating.
Well, it's a complex idea, but essentially superdeterminism suggests that everything in the universe, from the Big Bang to our choices about what to measure in a lab, is predetermined from the very beginning.
Well, it's as if the universe is following a pre-written script, and there's no true randomness or free will.
Hold on. So if everything is predetermined, doesn't that mean our experiments are essentially rigged? Like we're only going to get the results that were destined to happen anyway.
That's one of the controversial aspects of superdeterminism. It challenges our fundamental assumptions about cause and effect.
Right.
And it can be a bit unsettling to contemplate a universe where everything is predetermined.
I can see why that would make some people uncomfortable. It kind of feels like we're losing agency in our own lives.
It's a valid concern. And it sparked a lot of debate among physicists and philosophers.
Yeah.
Some find superdeterminism to be a compelling solution to the non-locality problem,
Okay.
as it removes the need for faster-than-light communication.
Okay.
Others see it as a bit of a cop-out,
Yeah.
a way of avoiding the truly bizarre implications of quantum mechanics.
So it's not exactly a universally accepted idea.
Definitely not. It's a highly speculative concept, and there's no experimental evidence to support it. However, it's an interesting example of how physicists are exploring all sorts of radical ideas to try and make sense of the universe.
It's a reminder that science is a process of exploration and discovery, and sometimes the most unexpected paths lead to the most profound insights. Speaking of insights, what are some of the key takeaways from this article that you think our listener should ponder?
One important takeaway is the importance of critically evaluating scientific claims, especially when they seem to challenge established theories.
Right.
It's easy to get caught up in the excitement of a new idea, but we need to remember that even in science, there are agendas, biases, and the potential for error.
Great, like that straw man argument we discussed earlier. It's a good reminder to look beyond the headlines and dig into the actual evidence and reasoning behind a scientific claim.
Exactly. Another key takeaway is that even within a well-established field like quantum mechanics, there are still profound mysteries and unanswered questions.
Like how to reconcile quantum mechanics with relativity.
Yeah.
Or what's really going on with this spooky action at a distance.
Precisely. These puzzles push the boundaries of our understanding and challenge us to develop new ways of thinking about the universe.
It's both humbling and exhilarating, isn't it? To realize that there's so much more out there to discover.
Absolutely.
Yeah.
It fuels our curiosity and inspires us to keep asking questions, seeking out new knowledge, and pushing the limits of human understanding. What excites you most about the field of quantum mechanics from what you've learned today?
What really gets me is this idea of the many worlds interpretation.
Okay.
The thought that every quantum decision creates a new universe, a whole new reality branching off from our own. It's just so mind-boggling. It makes you wonder about all the possibilities that might exist out there in the multiverse.
It's a captivating idea, isn't it? Even if it remains a theoretical concept, the implications of MWI are truly awe-inspiring. But even setting aside the multiverse, just the fact that we can describe the universe with such precision using quantum mechanics is remarkable. Think about it. We can predict the behavior of particles with incredible accuracy using equations and principles that seem completely counterintuitive to our everyday experience.
Yeah. It's a testament to the power of human ingenuity and our relentless pursuit of understanding the world around us. It's almost as if we're deciphering a secret code that unlocks the mysteries of the universe.
That's a beautiful way to put it. And this deep dive has been a journey through some of the most perplexing and profound chapters of that code.
I think it's time we start wrapping up this deep dive and offer our listeners some resources to continue their exploration of these fascinating topics. What would you suggest?
First and foremost, I highly recommend diving into the source material for this episode, the article we've been discussing. It's a brilliant example of how complex scientific ideas can be presented in a clear and engaging way without sacrificing accuracy or depth. You can find a link to the article in the show notes.
And for anyone who wants to delve even deeper into the world of quantum mechanics, I would recommend checking out the author's free online course. It covers a wide range of topics, from the fundamental principles to some of the more mind-bending interpretations like MWI. They even use visualizations and quizzes to make the learning process more interactive and fun.
That's a fantastic resource. It's incredible how much high-quality educational content is freely available online these days.
It really is. It democratizes knowledge and makes these complex subjects accessible to anyone with an internet connection and a thirst for learning.
Before we conclude this deep dive, I'd like to leave our listener with one final thought-provoking question to ponder. If, as the many-world interpretation suggests, every possible outcome of every quantum event actually occurs in some parallel universe, what does that imply about the nature of choice and free will in our own reality?
Whoa, that's a deep one. It makes you wonder if our decisions truly matter, or if we're just playing out a predetermined script on a cosmic stage.
It's a question that philosophers and physicists alike have been grappling with for decades.
Yeah.
And it's one that ultimately leads us to contemplate the very meaning of existence itself.
It really makes you think about more than just science. Like, we're talking about reality itself, free will, what it all means.
Exactly, and that's what makes this field so captivating.
Yeah.
It really pushes us to think beyond our everyday experiences, confront these mysteries that are like at the heart of the universe.
Absolutely.
Let's not forget the practical side of things.
Right.
Where can our listener go to learn more about this and keep going with their journey of discovery?
Well, like you mentioned before, the article is a fantastic starting point. It's really well written and gets these complex ideas across. We'll make sure to include a link in the show notes. But beyond that, what other resources would you recommend?
For those who are ready to dive deeper into quantum mechanics, I highly recommend the author's free online course. It covers all the essentials from wave functions and superposition to Bell's theorem and the measurement problem.
Okay.
They even use visualizations and quizzes to make it more engaging and interactive, which is always a plus.
That sounds like a great resource. I'm always amazed at how much high-quality educational content is available online these days.
It really is. It's a testament to open access education and the desire to share knowledge.
Yeah, and I think we've given our listener plenty to think about today, from the many worlds interpretation to the mysteries of momentum conservation and the challenges of reconciling quantum mechanics with relativity. We covered a lot. Any final thoughts you want to leave our listener with?
Oh, we have, and we've only just scratched the surface of this fascinating field. There's so much more to explore, and I would just encourage our listeners to keep asking questions, challenge assumptions, keep seeking out new knowledge.
I love that. Curiosity is what drives scientific progress. Never lose that sense of wonder and awe when it comes to the unknown. So to our listener, we say this. Keep exploring, keep questioning, and keep that spark of curiosity alive.
Yeah,
Because who knows what incredible discoveries are waiting for us.
right.
That's it for a deep dive into the world of quantum mechanics and the multiverse. Until next time, stay curious and keep those brains buzzing.